Yes, I think maybe we can start. I think we have people have joined.
Yeah.
So, okay. So
Okay,
welcome, welcome everybody to this week's Majorana-Raychaudhuri seminar series. We have two seminars this week. So the first seminar is by Mian from Krakow, and he's going to talk about primordial black holes from null energy condition violation. So let's begin. I will send you a reminder when 5 minutes are left.
Okay, thank you very much to invite me to give a talk. And today I will going to talk about a recent work from me and also my collaborator. Because I once asked Anish whether you need some more background introduction or not. So I will in this talk I will mostly I will somewhat introduce a little bit more about the background of the studies, and please feel free to interrupt and ask me if you have any questions. Okay, so let's start with uh, I guess somewhat you will know this history of our universe, right? So we have a standard Big Bang cosmology. I think somewhat you may know that, and we have a lambda CDM model as a leading paradigm of the thermal history of the universe. And today, we will talk about some physics in the primordial universe. That is, so somewhat people would call it a pre-Big Bang stage, in which the energy scale is very high, and the universe is assumed to experience quasi-exponential expansions called the inflationary stage. So the idea is that we have the relic from the early universe. So first of all is the cosmic microwave background, which is universally presented in our universe, and which is detected to have roughly 2.7 Kelvin at today, and almostly homogeneous and isotropically presented. So the measurement of the CMB temperature anisotropy is one of the most important discoveries in the study of cosmology. So the idea is that in the primordial universe, we have, oh, sorry, let's try to, if we can roll, okay. The idea is that in the very beginning of our universe, we have quantum fluctuations in the existing at the initial configuration. Then, as the universe expands, the initially quantum fluctuation, which is no longer in its vacuum state, and after the so-called horizon crossing event, these quantum fluctuations becomes classical, and these classical perturbations then interact with the um, uh, components of the universe, and then which interacts with the distribution of the photons. So since this quantum fluctuation is has a quantum origin, so we have to trace its physics through the correlation functions. So the anisotropy in the CMP temperatures can be studied by its correlation functions. One of the most important quantity is the so-called two-point correlation functions, which is let me know if I can show this figure, but first, which is precisely measured firstly in the year of 1991 by WIMP, and then we get a very precise measurement by the Planck collaborations, which indicates that the curvature fluctuations on large scales are almostly scale invariant. And we also have the so-called structure formation. The idea is that when those classical fluctuations, as we mentioned from the quantum fluctuations, forms local over-dense regions, which as the universe keep evolving, evolves into the current galaxies through some nonlinear effects, which forms the structure of the galaxies as we observed today. This is the physics of the early universe, and we will now talk to the inflationary cosmology, which is the phase before the standard lambda CDM paradigm, which is inspired by the puzzles of the conventional Big Bang cosmology. I believe the most mentioned problem is the so-called flatness problem and horizon problem. Although there is also some other kind of problems like the monopole problems, we are not going to talk about it today. So the idea is, let's first talk about this flatness problem. The idea is that we have observed a very flat universe, which we use this parameter omega k, which denotes the ratio of the effective energy density over the all energy density, which is simultaneously the matter content of the universe. And we find that by a joint observation with different physical processes like the CMB and BAO, and we find that this curvature of our universe is extremely flat, which naturally raises the problem that do we need a fine-tuned initial conditions for the lambda CDM paradigm for the universe to evolve to our current state. And we will also have the horizon problem. This problem is also related to the discovery of CMB. So we know that in the special and general relativities, the signals propagate at a limited speed. That being said, for any event, we can draw its past and future light combs. Any space-time events which is outside these light combs are casually disconnected with this event. And in the FRW matrix, which describes a homogeneous and isotropic universe, we can determine the causal connection by the so-called Hubble horizon, which is the inverse of the Hubble parameters. This is Hubble parameters, and we will later on also always use a dot to denote the differentiation with the cosmic time t. And for a co-moving observer, which the co-moving horizon is just the scale factor and multiples the Hubble and minus. And then we immediately find the problem that the space-time points of our universe is casually disconnected in the Big Bang or in the lambda CDM paradigm, but the CMB experiments told that those temperature and isotropies are statistically correlated. So this naturally gives us a question that why this kind of casually disconnected regions is in fact statistically correlated. So the solution of the puzzles relies on the so-called inflationary cosmology, which assumes that the universe, which initially is casually connected, but the conformal horizon shrinks in a pre-Big Bang phase, as we can say that we initially have all our universe to be casually connected, and then after the phase of inflation, this conformal horizon shrink. So at the epoch where the CMB forms, in this recombination stage, the particle horizon becomes small, and this origins appears to be casually unconnected. But this is which leads to the horizon problem. But this is actually not a problem because they are initially casually connected and they are statistically connected, correlated in this initial inflationary stage. And we notice that this also solves the flatness problem because the curvature, this quantity omega k, the difference from unity is proportional to this factor, and as the conformal horizon shrinks, this quantity also greatly shrinks down, leading to the smallness of the curvature, the curvature of our universe in today. So we come to inflation, which is a quasi-exponential expansion stage in the primordial universe. That being said, the universe, the scale factor of the universe evolves exponentially with respect to the cosmic time, where this h is a Hubble parameter, which is roughly a constant. And so one may ask why the scale factor evolves in this specific form. Why not it behaves like some kind of power law function of t? Why we must have this kind of exponential expansion? The answer is that inflation can predict the nearly scale invariant curvature power spectrum. So we know that to study this, the CMB temperature anisotropy and also the formation of structures, we need to know the statistical properties of the perturbations of both the matter sector and the geometry sector. And then in that case, we have to use some kind of gauge invariant quantities to characterize the fluctuations from the background ones. Conventional people will use the curvature fluctuation, which is related to the effective Newtonian potential, and the geometric quantities as follows. And then after some kind of simple computations, people find that the correlation functions of zeta carries essential information for the primordial universe. For instance, one of the most important quantity in the universe cosmology is the so-called two-point correlation functions of zeta, which is defined as p zeta is defined as follows. After some kind of computations, we find that the so-called temperature correlations, which is this quantity, which can be precisely measured by the CMB experiment, which is this CTT is exactly related to the curvature power spectrum in these simple relations. And then there is another merit to consider the curvature fluctuations. So the story is that we know the CMB is measured as a recombination stage, which is a very relatively late stage of the universe. And we may wonder, how could it be connected to the primordial universe? The good issue is that the curvature fluctuations, sometimes we use this zeta, or sometimes we use R. They are defined slightly different, but on the so-called super horizon regions, where the wavelength is much larger than the Hubble radius, both quantities is almost identical, and most importantly, the curvature fluctuations remains almost conserved in the super horizon regions. Oh, sorry, so there is a typo. So, and then by the precise measurement at the recombination stage, and we can immediately connect the experiments at this stage to the two-point correlation functions at the very early universe, since its conservations. So, so we have already shown the measurement of Planck at the early universe, which gives us predicts a nearly scale invariant curvature power spectrum. So we will also have the physics of structure formation. The story is as follows. So firstly, we have the quantum fluctuations, which is unavoidably exist in the initial stage of the universe. Usually, these quantum fluctuations at the very beginning of the universe is inside the horizon. Oh, sorry. Like this, and as the universe expands in the inflationary stage, those fluctuations become stretched out, and once its wavelength is comparable to the Hubble horizons, these fluctuations become super horizon and converted to a classical perturbations at this horizon crossing event. And when the universe evolves, and the classical perturbations re-enter the horizon and to become causally connected. This forms the local overdense regions, and after some kind of nonlinear evolutions, these local overdense regions forms the galaxies we live today. So after some kind of straightforward computation, we find that the power spectrum of this local overdensity, which can be directly measured by experiments, is related to the curvature power spectrum in a very simple manner. So, so this is the basic idea of the primordial universe. Its physics, and we also talk about the most important quantities of in that field. So up to now, is there any questions? Is it clear? Well, so let's continue. So then let's talk about a bit about inflation. So in inflation, the curvature power spectrum, it has a very simple form. So I just omitted the computations, but this can be in principle done by very quick, straightforward computation. So it is related to only two quantities. So one is the Hubble parameters, which denotes how the expansion rate of the universe, and another quantity is called the slow roll parameter, which characterize the changing rate of the Hubble parameters. Since in the inflationary stage, the Hubble parameter is almost the constant, this slow roll parameter must be much smaller than unity. And we can immediately see that the inflationary stage not only provides a natural solution to flatness and horizon problems, and most importantly, it also predicts a nearly scale invariant curvature power spectrum, which is confirmed by the CMB and large scale structure observations. And now we come to today's topic, the formation of primordial black holes from primordial fluctuation. The idea is quite simple. So we have talked about the story of structure formation. We have primordial fluctuations, which form the dense regions, and which finally evolves into the galaxies. So we may straightforwardly ask if this primordial fluctuations, is a bit stronger, and we have a more dense regions. Can these regions forms finally collapse to a black hole? The answer is definitely yes, and they are called primordial black holes. This idea is actually found already by Hawking in the year of 1971, but the problem is that after this foundation in the early 1970s, there is almost, I believe, 40 years where the idea of PBHs are not attractive from people, and it is only in the in the past decades that the discussion of PBH arise. The problem is that the abundance conventionally the abundance of PBH is very small. So here this is a brief introduction of how to compute the abundance of PBH in a standard formalism. But we can get a very naive idea about it. So we know that we have the curvature fluctuation on the CMB scale to have a fixed value, and we know that especially in the LS value, this amplitude of curvature fluctuations would lead to the formation of galaxies. And we know that black hole is astrophysical bodies which exhibit a very strong relativity region. So if we want the overdense regions to collapse into a black hole instead of galaxies, then the curvature fluctuation must be much larger than that on the LSS scales, and which is shown in these figures. And we can see that if we were to form PBHs on some smaller scales, then the amplitude of curvature fluctuation must be at least 10 to 3 order times larger than that in these LS scales. And then that means we need to enhance the P zeta on certain scales, which is quite a different task because inflation is already a very good models of primordial universe, and we will need to ask why we want to let's ask the universe to have some non-inflationary phase to enhance the curvature fluctuations, just to simply to get some PBH. So we need some motivations, and recently we know that there are a lot of motivation, lot of papers in PBH. People are doing this in a very, it's become a quite hot topic because mainly for the following two reasons. The first reason is the possibility to expand the supermassive black holes. So we know that the astrophysical black holes have typically a typical mass ranging from 5 to 100 solar mass, and on the other hand, the mass of PBH spans a quite large range, and in principle, this can range roughly 40 orders of magnitude, and since we have already observed the supermassive black holes in the, let's say, for instance, in the center of Milky Way with the mass to be 10 to 6 solar mass, and in the galaxy M87 with the mass 10 to 9 solar mass, and which is quite difficult to be explained by astrophysical black holes. So it is naturally to expect that since the mass of PBH can span this large range, can we use PBH to explain the existence of supermassive black holes? And also another reasons which I believe this is mostly explored by those PBH studies is that PBH might be a candidate for dark matters. Well, this idea is actually proposed also in the 70s, but not that well accepted at that time. The merit is that we do not really need any new physics beyond the standard model of particle physics. We do not need to introduce any fundamental particles. Instead, we may only need we may only need PBH. The advantage is that the measurement told us the dark matters are composed by both baryonic and non-baryonic contents. So we know that the popular candidates of dark matters like the metals is purely baryonic, and the WIMPs are purely non-baryonic. And in principle, PBHs can potentially exhibit both baryonic and non-baryonic natures. And that means PBH can potentially constitute the whole fraction of dark matters and becomes the solution of the dark matter problem. And also we have, it is argued that we have the evidence from LIGO that PBH can be a reason for the observed LIGOs, which is discovered shortly after the LIGO event and receives a lot of attentions. And so we see that the PBHs can have such kind of merit to solve the problem of supermassive black holes and also become the dark matter candidates, despite it might need some fine tuning. And this is, I believe, this is the most well accepted motivations to study PBHs. So this is a brief introduction to the physics of PBH. So, is there any questions in this part? Well, maybe we should continue. So then, as we suggest, if we want some PBH formation, we need to enhance the curvature fluctuations. So when we already talk about that, the curvature power spectrum in the inflationary stage, it has these simple forms, and the CMB observations tells that this P zeta is roughly 10 to minus 9 at CMB scales, but to have PBH formation, to have sizable PBH formations, we want this P zeta to be enhanced to the order of roughly 10 to minus 2. So from this simple expression, it seems that we have two options. One is to increase H at some certain scales. Another is the decreasement of the slope parameter epsilon, also at a certain evolving stage of primordial universe. Well, of course, there are also alternative mechanisms, but that would not be our focus today. So let's talk about this, the idea of the decreasement of epsilon. Actually, this idea is established in the framework of so-called ultra-slow roll inflation. So the idea is very simple. We want epsilon to be decreasing. So sometimes the second slope parameter eta, which is defined in a dimensionless manner, must be negative. And we observe that there is a very natural way to get this feature. That is, we introduce a very flat potential such that this V prime is 0, almost negligible. Then this simply gives us a reduced equation of motion for the inflaton, which gives eta to be roughly -6, in which the slope parameter epsilon can decrease as we expected. Well, so there are a lot of studies on the formalism of ultra-slow roll inflation. So I will simply give you two figures from a very old paper. Of course, this paper is very old and not such updated, but I would just give you a feeling that this is the evolvement of the slope parameter, and we observe that the profile of curvature power spectrum is roughly identical to the inverse of epsilon h, right? As you can see, this part is scale invariant, and when the epsilon h slower parameter epsilon shrinks, the power spectrum increases, and so p zeta simply has a similar profile as the inverse of epsilon h, which confirms our intuition of using this using this formula to estimate the curvature power spectrum. Now we immediately have a problem. Why not we increase h instead of the decreasement of epsilon to get PBH formation? The problem, we can look at this problem at a very simple evolution. So we have the Friedman equations, which characterize the evolution of the universe. And to have a parameter to be increased, we must have this right-hand side to be negative. That means we must have the null energy condition to be violated. The problem is that once you violate the null energy conditions, you will probably trigger either the ghost instability, which means that these prefactors, to be negative, so you have a action to be unbounded from below, or you have a negative sum to be squared, which gives you a gradient instability. A gradient instability just means that the curvature fluctuations either grows exponentially or decreases exponentially, because this CS becomes now imaginary, and then both cases is not desired by us. So we can have a very brief look at why this problem happens. So if we work in this so-called this kind of actions, and after some straightforward computations, we see that if we have the violation of non-energy conditions, you multiply these quantities, and you will find that these quantities is negative. So you will trigger either the ghost problem and the gradient instability problem. So in fact, the violation of null energy condition is a very important topic in the study of cosmology, except for our naive idea that we somewhat increase Hubble parameter to get PBH. The violation of null energy condition also finds its applications of the so-called non-singular cosmology, which to avoid the cosmological singularities, which is also important in the study of wormhole physics, where a very straightforward evaluation shows that to have a wormhole, you will also need to violate the null energy condition. So people just want to search for a healthy realization of the null energy condition violations, but unfortunately, people find that even if we introduce actions in this kind of complexity, this is called the Hondesky theory, or sometimes generalized as Galileans, then we still have the no-go theorem, which prevents us to have a healthy non-energy condition violations. And our study is quite simple in ideas, but the main problem is the technical problem. That is, we want to violate the non-energy condition healthily, and this is recently. I would not say recently, because it's already 5 to 10 years ago. So firstly, people find the healthy extensions beyond this Hondesky theory. That means you can introduce a gravitational action, which is even more complicated than this one. And then we find that eventually in this kind of complicated actions, we can have a healthy NCV in cosmology. And basically, this is just my paper, the first paper in my PhD studies. And now I can show you that although we finished this, solve this problem, the code is that we have to introduce the very, very complicated, very involved actions in this form. Now, since we finally solved the technical issues, it's time to reconsider our proposal. That is quite simple. So we just introduce an intermediate NCV phase in the inflation stage. That means we have the first inflation, and then when at certain time the NC is violated, which boosts the Hubble parameter to a certain size, and then we have a second inflation phase, which after some straightforward computations gives us the peak in the curvature power spectrum. Here we just illustrate the curvature power spectrum in the 4 specific model parameters in our paper. So, and to validate NEC, we just need this kind of actions, which I give you an example, but of course we need to carefully design the coupling functions in both here and here. And we will also need some certain designations of the potentials. But generically, this action itself is not that involved. The problem is that to eliminate the gradient stability problems, we need to introduce very complicated actions. In our paper, we just simply insert EFT operators. Although it's proved that these EFT operators can be casted into a covariant form with a very complicated expressions. The idea is that these operators merely contributes to the sound speed of scalar fluctuations in this manner. So with certain choice of this form of EFT parameters, we can eliminate the gradient instability problems without altering the other physics, like the background evolution, and we have this p zeta, right? And which can be after a very standard computation can give us a sizable ratio of PBH. Here we just illustrate this PBH abundance in 4 characteristic mass scales of PBH. Okay, so as we have introduced, we have realized our naive idea of the PBH formations in really complicated actions. So we have to ask, what's the merit of our models? So the first one is that we proved in our paper that our model is free from the recently very concerned one loop problem in the USR scenario. Well, but the problem is that this problem is still in debate, although it, as you can see, this is proposed in the year of 2022, but there is still papers appear in nearly, basically this paper is just published in this October, saying that the USR scenario indeed do not have the one loop problem. So this is topic is still highly in debate. So we should not talk about it too much today. The real merit of a model is, I believe, is it provides distinct predictions on high frequency gravitational wave band. So let's somewhat review the gravitational waves. In the standard PBH formation scenario, we have such large curvature fluctuations on certain scales, which means that it's nonlinear interaction between zeta and between curvature fraction and the tensor modes become important, which gives us a sizable secondary gravitational waves. We call it the scalar-induced gravitational waves. And also, I just subtract the figures from the same paper in the USR part, which we see that we have the energy density of the induced SIGW is roughly also have the same profile as the curvature power spectrum and is potentially detectable in the future feature gravitational wave detections. And in our model, instead, in addition to the scalar-induced ones, we will have a primary gravitational wave. The idea is that the tensor power spectrum in inflation is of the form which is dependent also on h squared, but not dependent on the several parameters. So in USR scenario, we change the several parameter change, but the Hubble parameter is almost invariant. So we will get a very trivial PT in all scales. But in our scenario instead, the Hubble parameter is boosted. So in principle, the primary gravitational waves on smaller scales is enhanced. So our scenario would predict a sizable PGWs on high frequency band. This means that our model is promisingly falsified in comparison with USR in the future. So this is a figure showing that predictions for gravitational waves in our models. The solid ones is the primary gravitational waves, while the dashed one is the scalar-induced secondary gravitational waves. And we see that the primary gravitational waves can in principle be forced by this PTA, right? If the PBH is formed in certain scales, and also which is also sizable on higher frequency bands. And we should especially concern on these brown cases where the primary gravitational waves is promisingly detectable in the future project like LISA, Taiji, and
we have 5 minutes left.
Yeah, sure. I will quickly end it. So, and on the same time, the induced ones can be detected in a higher frequency band by BBO and DeSico events in the future, which is distinct from the USR scenarios. So let's conclude the talk. So in this work, we have proposed a new PBH generation mechanism from the idea of non-energy condition violations. We can provide a robust model constructions utilizing the recent development of modified gravity studies and provide robust, healthy models which is instability free, and we also have the unique predictions on higher frequency bands of gravitational waves, which means our models is testable in future astrophysical experiment. So that's my talk today, and thank you again for inviting me to the seminar.
Thanks for the nice presentation. Anybody in the audience, any question, please unmute yourself and ask.